All right, so I should be recording at this point. So what is Unit 4 about? First of all, I wrote some quick notes to remind myself of what I wanted to say because it's early in the morning. So Unit 4 is actually about mixtures. It's about states of matter for all different materials. So it's about mixtures. It's about states of matter. And we're going to do an intro to chemical reactions. So the simple version of chemical reactions, we'll be doing more complicated chemical reactions in Unit 5. Unit 5 will all be about chemical reactions. So Unit 4, we're going to be looking at how do mixtures form. For example, homogeneous mixtures versus heterogeneous mixtures. We're going to be looking at what dictates if a compound dissolves in water or not. How do we know? Intermolecular forces is actually the quick answer, what we're going to learn today. How do we know what materials exist in the solid phase, the liquid phase, and the gaseous phase? For example, why is water a liquid? Carbon dioxide is a gas, although carbon dioxide is actually heavier than water. The mass of carbon dioxide is heavier than the mass of water, but water exists as a liquid, which means it's more condensed, whereas carbon dioxide exists as a gas. Why is that? That's also going to be partially answered in today's lesson and fully answered over the next several lessons. So the state of matter, including the melting point and the boiling point for substances we're going to be looking at in this unit. And then we're going to look at an introduction to chemical reactions, meaning we're going to learn how to balance equations. If you've done that before in physical science, we'll be ending this unit with balancing chemical equations, and we'll be looking at how to determine the states of matter for different chemicals in chemical reactions. So that's Unit 4. It's a short unit. It's kind of like a bridge unit because where we're going to go after this is straight into chemical reactions, which is phase 3 of the class. Chemical reactions will be Unit 5, and then quantitative analysis, which is the math, is Unit 6 in this course. So this is where we're going, and this is where we're at. Unit 4, Lesson 1, Intermolecular Forces. It's going to look a lot like the last lesson because it is a lot like the last lesson. It has to do all about polarity, but now we're going to be looking at how do molecules interact with each other. If you're going to move on and study biology, I'm sure you'd like to know why do the two strands of DNA, how are they held together? By an intermolecular force that holds the two strands of DNA together, that is DNA and not RNA, which is single-stranded. So everything in this lesson is important for understanding a lot of what's going on in science. Notebooks are over there. So we're going to go ahead and get started now. Unit 4, Lesson 1, Intermolecular Forces. You've already watched a little bit about it. This is a very visual topic because you have to draw molecules. So that's why I wanted to have you start with the video so you could kind of put together the senses of attraction of what's going on. The one force we're not really going to talk about today, maybe two, we're not going to talk about ion dipole today, but you saw it in the video. That's when you have an ionic compound dissolved in water, it's an ion dipole force. And we're not going to really look at ion-ion today. We're going to be looking at covalent compounds only for today's lesson. So what do you have to do? You don't have to write this down, but you'll notice that this is the end of the last unit. Topics you're going to need to remember for this lesson, you're going to need to remember how to determine valence electrons from an element's position on the periodic table. You're going to need to remember how to draw Lewis structures yet again, because drawing Lewis structures will yet again be on this next unit exam. It's not going away. And then finally, you're going to have to know how to determine if a molecule is polar or not. You are no longer going to be given numbers, no electronegativity chart. You will have to determine based on the shape of a molecule if it is polar or not, based on the instructions I had given in that lesson. Welcome back. Are you still good to take the quiz till 8:30?
What?
The quiz you're taking? Are you still good to take it till 8:30?
I should be there.
Okay. So these are some of the common molecular shapes. You do not have to write these down, but you were supposed to memorize these. There's a couple of them that are always polar. Do you remember which ones? Which are always polar. That's pyramidal. Why? Both have unshared pairs of electrons. So if you have unshared pairs of electrons, your molecule is totally going to be polar. So you have to determine that from your Lewis structure and look at your central atom. Linear, trigonal planar, tetrahedral may or may not be polar depending on symmetry, whether your molecule is symmetrical or not. Another way of saying that is the elements that surround the central element are the same, then it's symmetrical. If they're not, then it's not symmetrical. So then you're going to want to start by writing this down. How does bond shape predict polarity? You should write this down even though it's from a prior lesson, because this is the predictions you're going to need to make. So when you have electrons or pairs of electrons, to be clear, pairs of electrons alter the shape of a molecule in such a way that the groups of atoms do not pull in opposite directions anymore. And so this is why when we have something that is bent, the way you have to envision that molecule is you have something at the top, we'll use water as an example, and something at the bottom. And so the hydrogen atoms in water are not pulling in opposite directions. They're both pulling down, where the oxygen is pulling for electrons up. The shift in this bond angle is what actually makes your molecule polar. You're not going to have to memorize the numbers, but you have to know the idea. You had to memorize the numbers for the last test. And then you should also remember, to predict a polar molecule, what you're actually looking for is an uneven pull of electrons. Your molecule is not symmetrical. Or you've got unshared pairs of electrons on the central element in a simple molecule. By simple molecule, we mean one central element. You should also recognize the dipole sign because you're going to need it today. This means partial negative and partial positive. I'm going to pause to give you some time. There's a lot here, but this is from before. And then let me move forward here. So what we're going to be looking at today is we're going to be looking at 3 different forces of attraction between molecules. So the questions are, how are molecules attracted to each other? And there are many forces. We're going to be looking at 3 of them today.
Just to try out, she doesn't understand it. Yes,
You are also going to have to remember, in general, what elements are more electronegative and what elements are less electronegative. It would serve you well to memorize the trend back in unit 2, that electronegativity increases as I go up the periodic table and I go from left to right. And you should also, at this point, memorize that the 3 most electronegative elements, you're not going to have the numbers to work with, are fluorine, oxygen, nitrogen. Meaning if you have any other element combined with either fluorine, oxygen, or nitrogen, which oxygen and nitrogen are super common to use in molecules because all of your biological molecules, for example, have oxygen and or nitrogen. So if you have any element combined with oxygen, nitrogen, or fluorine, those elements are going to be the one that hog the electrons. The electrons are going to shift to. Are you? If you need more time, you can have it because we were off. Don't forget there's also tutoring, not for Prius, but there's tutoring today that you can come to make up a test. Hi, good morning. Did you get counted in the front? Yeah. Okay, go ahead and get signed in. We're on Nearpod, so join in either through the Google Classroom. Okay, so I'm giving you a little bit more time before I move forward. What we're going to be doing is we're going to be looking, like I said, at 3 different intermolecular forces and how to predict them. And I believe we're going to do them from weakest to strongest. Yes. And you finish her. Moving forward in about 30 seconds. If you take a picture, please make sure to do so now. That'll be recorded. After school, I'll be posting it. All right, so let's go ahead and continue at this point. Before, go ahead and write these down in your notes and see if you remember. It's literally what we just did on the test last class. Are each of the following molecules polar or non-polar? So go ahead and write these 3 down in your notes and see if you remember how to predict this. Polar or non-polar. Yes. Yes. We're going to go over each of these quickly together so that we can get to the new. The first step to determine polarity is to draw the Lewis structure. This number down here means you've got 2 of that element, so 2 atoms of hydrogen, right? And so you write them next to each other. Then you do the valence electrons. At this point, we need to go quickly because we have done this many, many times together, like 30 at least. So each hydrogen has 1 valence electron, and then we connect the bonds together. And this is H2. The question is this polar or non-polar? Non-polar means that electrons are shared evenly, whereas polar means that they're not shared evenly. So, yes, correct. So this is non-polar because each hydrogen is pulling, each hydrogen's nucleus is pulling with an equivalent charge in 2 opposite directions, and we say that neither hydrogen wins the battle for electrons. Because of that, the electrons must be shared evenly. This is a non-polar molecule. NF3. 1 nitrogen, 3 fluorines.
It is polar.
Correct. And this you can predict simply from the shape, or when you draw out the Lewis structure, you should say because there is an unshared pair of electrons on the nitrogen, this actually alters the shape where the nitrogen's on the top and the 3 fluorines are on the bottom. And the way to understand this is the fluorines are going to be pulling with a stronger force than the nitrogen, so this will be indeed polar. How do we know without looking at the numbers? Because you're supposed to memorize fluorine is the most electronegative element, and that is the trend. As I go up and over, electronegativity increases. And then CH3OH. This is polar or non-polar? Polar. Anytime you have a bunch of carbons and hydrogens and you've got a super electronegative element somewhere in there, it's not symmetrical. This is going to be a polar molecule. The oxygen would be the partially negative end, and everything else on the other two sides would be the partially positive end, meaning the electrons are moving towards the oxygen. So this is also a polar molecule. This is what we learned before. This is nothing new yet, but it's the starting place for where we're going to go. Forward on your putt. All right, so now we're going to go to what's new. Intermolecular forces. So you should write this down. Intermolecular forces. What this means is the force of attraction between substances. Substances is the chemist word for stuff. If I don't want to specify if I'm talking about a molecule, an atom, an ionic compound, I can call it a substance and it covers everything. And so, although today we're looking only at molecules, and we'll be looking, I think, at atoms as well, this also, intermolecular forces, also covers all types of substances. So when we're talking about intermolecular forces, we're now expanding past one molecule. We're now looking at how do molecules interact with each other. So that's why I said this is the beginning of the topic of mixtures, because we're going to be mixing things together. We're going to be making solutions. We're going to be looking at different types of mixtures as we go through this unit. And so the first thing we have to understand is how are substances attracted to each other? And it's through this idea, the force of attraction is called the intermolecular force. And you should write down, this is for molecules, the 3 types of intermolecular forces you're going to be responsible for knowing. And they are listed here from weakest to strongest. So you can write them down in this order, where dispersion is the weakest. Just to be clear, and hydrogen bonds are the strongest. And you'll see in the diagram, you don't have to write down the diagram here, but the diagram is showing you intermolecular forces. The green arrows represent forces of attraction. The gray arrows represent forces of repulsion. And you'll notice that positive ends of molecules are attracted to negative ends of other molecules. Back to the basics in Unit 1, that you have to understand how charges work. Negatives repel, like charges repel, and opposite charges attract is what's going on again today. It's almost time. Do you want to start heading downstairs? And you can come back and meet us later. go ahead and get that up. We're moving forward shortly. I'm giving you about 30 more seconds here. This is an introduction to what intermolecular forces are. So we're going to take a look today at each of these three forces and how to predict them, what they are and how to predict them. All right, force number one, here we go. The weakest force that exists, but exists for almost all substances, is called dispersion force. So you can write number one. There's three of them we're learning today of the dispersion force. And this is the weakest type of attraction that exists between molecules. So everything here is important. A dispersion force will be present if an atom or a molecule has electrons. So the requirement for a molecule or a substance to have a dispersion force is that it has electrons. If a molecule has electrons, well, electrons move. And in the electron cloud, the electrons can move temporarily to one side of the atom or molecule more than the other. And so we end up with something called a temporary dipole. Temporary means doesn't last very long. As long as there are electrons, the electrons can shift in the molecule. These are the strongest forces that nonpolar molecules can exhibit, and single atoms. So nonpolar and single atoms can only have dispersion forces because they have electrons. Electrons move, they can temporarily shift from one side of the atom to the other in the electron cloud, and that temporary shift will cause there to be a negative side and a positive side to the molecule. And so what you're going to have to predict is if you have a nonpolar molecule or if you have a singular atom, the strongest force of attraction it can have is dispersion forces, which honestly are extremely weak because they're only temporary. And so most of the time there are no forces of attraction or very close to no forces of attraction between nonpolar molecules. So weak attraction means barely attracted. Not really attracted very much. But the requirement for something to have a dispersion force is that it has electrons. Is there any substance that doesn't have electrons? Is there anything that doesn't have electrons? I mean, I'm being pretty clear that like atom molecule has electrons. If you look at the periodic table, everything has electrons. So is there anything that doesn't have a dispersion force technically? Well, what if we took hydrogen? What if we took hydrogen and we took away its one electron, right? Hydrogen plus one is a thing. That exists. This has no electron. This is the only thing. No. It is something very famous though. It is an acid. So it's highly corrosive and destructive, but it's not explosive. H plus 1 has no electrons. So that's literally the exception to what has dispersion forces. Everything else has dispersion forces.
Then wouldn't it like stable?
Because hydrogen only has one. It's by definition an acid. You may want to write that down because we have a whole unit on acids later this year. Everything else besides that, though, actually has electrons that we know of. Even H2 table that we know of has electrons. The only thing that naturally exists, I should be clear, that doesn't have electrons is H+1. Naturally exists in nature. Hydrogen is a nonmetal that has low electronegativity, so actually loses an electron, just like a metal. All right, so that was force number 1. Make sure you have it down. It's the weakest force that can exist, and it is the force that exists in almost all atoms and molecules and substances that exist. Everything has dispersion forces as long as it has electrons. And the whole idea of the force is that when electrons move, you get what's called a temporary dipole, which means you get a temporary force of attraction as a result. Second force. So this is number 2. I want to write it down. Number 2. Second force you need to know is called the dipole-dipole force. Well, based on the name, you may already know what the requirement is for the type of molecule that would have a dipole-dipole force.
Yeah.
What type of molecules, when they interact, and you should also write the example here. The example. It has to have the dipole. And this right here, the dashed line, dash, 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 that is the force, BH. Right, so I'm about to fill that in. The requirement for a dipole-dipole force is that the molecule has a permanent dipole. What type of molecule always has a dipole, a positive end and a negative end, or an arrow going towards the more electronegative element? The molecule would have to be polar. You've got to have something that has a partial positive, partial negative charge. So you've got to have something polar in order for it to exhibit a dipole-dipole force. This is the second force, meaning that it is stronger than a dispersion force. It is a stronger force of attraction between substances. And so they're called permanent instead of temporary is another way to understand it, meaning that the charges are always there. Whereas in a temporary, a dispersion force, the charges are only there for milliseconds. Is your computer working? Is your computer working? No, so you'll have to get on with your phone. Okay. And so you'll note another thing here. It says the larger the dipole, meaning the more polar is another way to say it. The more polar your molecules are, the stronger the force of attraction will be. So the greater the electronegativity difference, the stronger the dipole, the greater the attraction will be. And so the example here, you've got 2 HCl molecules. The Lewis structure or the shape for the first one's drawn here. The shape for the second one's drawn here. It's not the full Lewis structure because it's missing the electron, but we can fill those in on chlorine. And then the idea is that because chlorine's more electronegative than hydrogen, this is a polar molecule. Chlorine is more electronegative. You'll have to predict that yourself. How would you predict that? Chlorine is right next to fluorine in comparison to hydrogen that's way over there. So chlorine is more electronegative, so the electron should be shifting towards chlorine. At this point, you do have to use the dipoles. You have to use the partial positive and the partial negative side to show the attraction instead of the arrows. And so the final thing I want to bring up again is the dashed line I was saying is the force of attraction. That's the actual force of attraction. We show it with a dashed line. It's important you do this with a dashed line instead of a straight line. Because the straight line tells us that these atoms are covalently bonded together. The dashed line just means that they're attracted. Different molecules are attracted to each other. Yes? Yes, I believe it's available. Welcome. All right. We have one more type of force of attraction. I'm pausing. Remember, I told you there's 3 we need to know about. and then we're going to do examples and predictions. And there will be some questions for you to answer on Nearpod. I'm moving forward to the last one on Nearpod. If you're ready, I'm going to move forward shortly in about 30 more seconds. If you need to take a picture, please do so now. This is, do you need to take a picture? So the last one, number 3, that we're covering today. The third force of attraction between molecules is called the hydrogen bond. If you move on to marine science, this is the one that Ms. Jadai is going to talk about all the time. If AS Marine Science is your choice. You also need to understand hydrogen bonds for AS Biology and for AS Chemistry. Hydrogen bonds are the strongest, it's kind of weird, they're the strongest of the weak forces. All 3 of the forces we're covering today are considerably weak forces of attraction. However, hydrogen bonds are your special, stronger dipole-dipole force. And so the requirement for molecules to be attracted by hydrogen bonds is not only does the molecule have to be polar, it also, so I'm going to write polar and. So and is underlined. You've got to have a hydrogen connected directly to a fluorine, oxygen, or nitrogen. Because fluorine, oxygen, and nitrogen are the 3 most electronegative elements. This gives you a stronger than normal dipole-dipole force, which gives special properties. This enhances the properties of the molecules that have hydrogen bonding and gives water, actually, when you go study water, many of its special properties, like its high melting point, its high boiling point. Its cohesive and its adhesive properties have to do with the fact that it hydrogen bonds, that it has this special, stronger force of attraction between water molecules. And so you'll see here, and you'll want to write down the example for water. This looks very similar to what we had before. It looks just like a dipole-dipole because it is just a dipole-dipole force that is stronger. And so here is, we would label this the hydrogen bond. The hydrogen bond is the attraction between the partially positive hydrogen of one molecule, and in this case, a partially negative oxygen of another water molecule. And it can exist if you've got molecules that have hydrogen that's directly connected to fluorine, oxygen, or nitrogen. Now you may also want to write, it's up to you, this diagram over here, because it tells you that there's a difference. The hydrogen bond is the dashed line, that's the intermolecular force, whereas the bond that connects oxygen and hydrogen together in water, that is not an intermolecular force, that is a regular covalent bond that we already learned how to draw last unit. That holds the molecule together. The covalent bond, I might want to point out, holds the molecule together, whereas the hydrogen bond, or the intermolecular force, attracts molecules to each other. The attraction of molecules to each other, that's the hydrogen bond. So they're 2 different things. The covalent bond is the line we draw on a Lewis structure, where the hydrogen bond is the attraction between separate molecules. And so what you're going to be asked to do, this is the last, I believe, of the main informational slides, the 3 types. What you're going to be asked to do is, given different molecules, you're going to be asked to predict whether their force of attraction is by dispersion. Yes?
Ms. Valina, I'm sorry to bother. Xavier Regalado. Can you come back for a moment?
No problem.
Thanks.
Thank you. Go back to the list. predict based on looking at molecules whether they're going to be attracted by dispersion forces, by dipole-dipole forces, or by hydrogen bonds. That's our goal today, is to determine which of the three forces molecules will be attracted by. You'll see some writing. Jose, you might want to take a picture real quick.
Yes.
You just came back from the bathroom. I'm moving forward in about 30 seconds. All right, so let's take a look at what we could be at. Predicts the strongest type of intermolecular force between molecules of the following. The first is PBr3. So the type of question you're going to be asked off of this lesson, the first type of question, is predict the strongest type of intermolecular force. Strongest type doesn't mean it's the only type that exists. For example, if a molecule has hydrogen bonding, well, it also has dipole-dipole, and it also has dispersion, because the requirement for a molecule to have dispersion forces is just that it has electrons. But this question is asking for the strongest type present. And so you technically have a word bank here. Your choices are what? Right, so you've got dispersion, you've got dipole-dipole, and you've got hydrogen bond. Those are your three choices. If you're asked for an intermolecular force, you will have to give one of those three. So PBr3, how would we determine which force we have? What's the first step? What should you do first? You should draw the Lewis structure. That again, yes, I told you this lesson is basically a continuation of where we were at heading into the next unit. Phosphorus goes in the middle, 3 bromines on the side. I draw them pretty quickly now. This is considered to be a level 1 question. Nothing too complicated here. What do we use the Lewis structure to determine? That's going to help us with this.
The geometrical structure.
Polar or non-polar, based on its geometry, or based on the fact that phosphorus has an unshared pair, right? Unshared pair tells me that it's polar or non-polar.
Polar.
This is a polar molecule. So the unshared pair tells me, the unshared pair on the central atom tells me it's a polar molecule. Dispersion forces are the strongest force for what type of molecule? Non-polar, right? Dipole-dipole is the strongest force for regular polar molecules. And hydrogen bond needs to be polar and hydrogen connected to fluorine, oxygen, nitrogen. So which one is true for PBr3? Quick way to know. If you ain't got hydrogen, you ain't got hydrogen bonding. Does that make sense? No hydrogen cannot be hydrogen bonding. So you've got a polar molecule, there's no hydrogen, this has to be. So that is our prediction. What does that actually mean? If I had a PBr3 molecule, right, which if I draw it correctly, it would be drawn like this. Phosphorus and bromine, it's hard to tell which is the negative end and which is the positive end, so you'd be given something more clear. Actually, bromine is more electronegative, according to the numbers. This is the negative end, this is the positive end. So if I have more than one PBr3 molecule, what this means is that another PBr3 molecule would be attracted in the following way. And then I'm going to use a different color. The positive phosphorus of one PBr3 would be attracted to the negative bromine of another PBr3. That's what the dipole-dipole intermolecular force is. attraction between two molecules. One of the last things you're going to be asked to do is draw the force of attraction, so that's why I'm showing you what to do now. But to answer the question, the answer was just simply dipole-dipole for this question. What about CCl4? What's the strongest force of attraction for CCl4?
So it's dispersion.
It's dispersion. Correct. And you can remember that because this is symmetrical. It's a symmetrical molecule. It's nonpolar, right? CCl4 is completely symmetrical. 4 chlorines pulling in 4 directions, all with the same power. So we call it nonpolar. And if it's nonpolar, the answer for our type of force, which would hold CCl4 molecules together, is dispersion, which means it's the weakest type of force. For dispersion forces, you would not have to write the force of attraction. You only have to do that for dipole-dipole and for hydrogen bonding with the partial positive, partial negative charges. Dispersion forces have very weak forces of attraction. There may be a partial positive, partial negative for a second, a millisecond, but it goes away. That's what we call a temporary dipole. So the only thing that holds it together at all is the fact that it has electrons, and those electrons. So dispersion is the answer for the second one. Got a couple more to work through, and then we'll take a look at the last thing. You'll have to practice examples of your own on your plot. Yes. Go ahead. HF. Next one, HF. What do we think is the strongest type of force for HF? Try it out. But it might be pretty apparent to you. It's very polar, yes. So what does it meet the requirement for?
Oh no, hydrogen bonding.
Right? Hydrogen bond. Because not only is it polar, it's hydrogen, which has a low electronegativity, connected to one of the 3 most electronegative elements. So if you see hydrogen directly connected to fluorine, oxygen, or nitrogen, this is called a hydrogen bond. Meaning if I had multiple HF molecules, they would be attracted to each other via hydrogen bond. OCl2. Fluorine has 7 valence electrons, oxygen has 6. Polar or non-polar? Polar. Because it's bent down like this, right? Polar. Polar means which of the 3 is the strongest? Is dispersion the strongest? Is dipole-dipole the strongest? Why not hydrogen bonds? Doesn't even have hydrogen. But it technically has to have hydrogen directly connected to a fluorine, oxygen, or nitrogen to be considered hydrogen bond. Because it has to be that electronegativity difference very large. To a carbon or a chlorine, so then it wouldn't be hydrogen. It has to be hydrogen covalently bonded to one of the 3 most electronegative elements. It's that difference in polarity that gives a special stronger dipole. So then this is dipole-dipole. Because it's polar. So are you still going to have to be able to predict if a molecule is polar or non-polar? Absolutely. But this time you're not given numbers. You're going to have to figure it out based on the shape of the molecule. All right, let me see where we're at in Nearpod to see if there's any practice questions yet. I know I have a couple. Yeah, there's a couple of questions up on Nearpod now. It shows me there's 5. Go ahead and see if you can answer these 5 questions. I'm going to give you about 4 minutes to go through them till 8:55. So there's 5 molecules, I believe, that are given to you. You have to determine the strongest force for each of them. pH3 is the first one. F2 is the second one. HF's the third one, which I think I already did. It's right up there. CH3OH and CH4. See if you can do each of these. This is for participation on Nearpod. Questions up on Nearpod for you to solve. It may benefit you to draw out the Lewis structure to figure it out. You're going to start to see all these lessons build on themselves. And so the strength of the intermolecular force is extremely important to be able to predict things like solubility, states of matter, melting points and boiling points, like what temperature does a substance melt or boil at, which is why we're learning this first. Yeah, welcome back. Oh, sorry.
Oh, sorry.
Yeah. I'll tell you the answer at 8:55 for each of them. It's 8:53, so you've still got 2 more minutes to answer on Nearpod before we move forward. Make sure at this point you are answering on Nearpod. You've got 1 more minute. Remember, it doesn't count against you if you get it wrong, but you do need to answer. To the best of your ability. Welcome back. All right, so it's 8:55, so I'm going to go ahead and share the answers. For the first one, pH3, that's a polar molecule, so you should have came up with the answer is dipole-dipole. So one was dipole-dipole. The second one, F2, that's nonpolar, so the answer for that one should be dispersion. The third one, HF, is literally on the screen. It is hydrogen bond, and yet not everybody got that correct, interestingly enough. Question 4, CH3OH. What is the strongest intermolecular force? You've got that hydrogen directly connected to oxygen, so it has to be hydrogen bond. And so then finally, the fifth one, CH4, that's symmetrical. It's nonpolar, so it should also be dispersion. So when we answer for intermolecular forces, there's one of 3 answers you should give: dispersion, dipole-dipole, or hydrogen bond. Because when we're talking about intermolecular forces, we're talking about forces of attraction. So now we've got one more thing to cover, and then you're going to have an exercise to do and a time to climb, which means you have a little bit of a competition today at the end of class. All right, this is the last thing I'm going to show you how to do, which I technically kind of already showed you, but let's go ahead and show it from scratch. It says to draw the attraction between the molecules below, and you are going to have a couple questions in your classwork/homework that you will have to do this as well. Draw the attraction between the molecules below, HF and H2O. What we mean by draw the attraction is you're drawing the intermolecular force. So you're going to draw the intermolecular force with dashes. IMF is the shorthand for intermolecular force. We don't want to write all of those words. We write IMF between the 2 molecules. HF, we've already drawn it, so I'm going to draw it quickly. HF. The next thing you need to do, so it's draw the Lewis structure. Write the dipole, which means partial positive, partial negative. You need to include what end of this molecule is partially positive, what end of this molecule is partially negative. Between hydrogen and fluorine, which one's partially negative? Between hydrogen and fluorine. Most electronegative element, right? So you put a partial negative sign on fluorine. And the least electronegative element is partially positive. You should do this for HF first. Now you're going to go ahead and do this again for H2O. But the reason why I didn't do them both at once is because if you understand what's going on, you may be able to figure out how to draw water. You need water to be attracted to HF. Which end of water would be attracted to HF, the oxygen or the hydrogen? Can you figure it out? Well, if we draw out the oxygen next to the fluorine, I'm just going to show you what happens. If you do this, you're going to say this, because oxygen's more electronegative and hydrogen is less electronegative. So you're going to want to erase this, by the way. I'm just proving what the answer is. A negative and a negative is not going to attract. They're actually going to repel. Remember, like charges repel, opposite charges attract. So we would actually want to organize this the opposite way, where the hydrogen is close to the fluorine and the oxygen's facing away. So I'm going to erase this.
Why couldn't the oxygen?
It could,
No,
and it will.
I'm saying with the hydrogen.
It totally can. So, and I mean, when you think about what's actually going on with water, it's going to surround. That's the whole process of dissolving. This water is going to surround on both ends. The positive end of water will attract to the negative end of your molecule that you're dissolving, and the negative end will attract to the positive. That is the whole process of forming a solution that we're going to later in this unit. But for this, at this point, we've just got to understand that an intermolecular force is that force of attraction. So the positive end of a water molecule, so hydrogen, would be attracted, because this is less electronegative, to the negative end, whereas, and I'll show the other side too if you want me to. You don't have to show more than two yourself, but I can show more than two. The attraction is this line that I'm writing. This right here is the hydrogen bond. So this is what you would have to do. Believe it or not, this is a type of question that shows up on an AICE chemistry exam and would be worth 3 or 4 marks to be able to show this process. It's not too complex if you understand what's going on. So look, you had mentioned, what if we had put oxygen attracted to the hydrogen? We could totally add another water molecule that way. You don't have to do this, but just to understand, molecules exist 3-dimensionally, so you could write them however you want around each other. You would want to write water with its correct shape, which is bent. Oxygen is negative, hydrogen is positive, and then the hydrogen bond would be the force of attraction between this electronegative oxygen of water and the positive hydrogen of HF. And so this is another hydrogen bond. So if you want to, you can write that out as well. All I'm going to ask for you to do is between 2 molecules. If you want to add more, you can. Because remember, molecules exist as millions and millions and millions. If you have a solution of water, tap water, you've got billions and billions upon billions of water molecules there. You don't just have them existing as one single molecule. You have a bunch together. So this is what you'll be asked to do. It's your turn. There's a question like this on Nearpod now. I knew it. I put one on Nearpod this morning. So on Nearpod, I would like you to see if you can draw the attraction between the following 2 molecules, water and CH3F. So on Nearpod, I'm going to give you 5 minutes again, and then we'll do the time to climb exercise. So on Nearpod, draw the attraction between water and CH3F. You gotta draw the Lewis structures, write the dipoles, and then orient the positive end of one molecule to the negative end of another molecule. So write the dipoles, and then what I had said but I didn't write is orient molecules in such a way where opposite charges attract. Got a few minutes to go ahead and draw the top on here. First, start by drawing your Lewis structures. You can do either one first, water or CH3F. I would do the CH3F first, and then just connect water to it. Water, remember, is 2 hydrogens and 1 oxygen. Hydrogen can never be in the middle of a molecule. I'm giving you a couple minutes till 9:05. Make sure you're drawing an answer on Nearpod at this time. Yes. I'm sorry? I don't. They didn't say on the announcements that I heard. I would try the media center typically. The first place to try. If they don't make an announcement. That's okay. I'm going to start by drawing the Lewis structure of CH3F. You can check to see if you got the answer right. It's 9:05, so I'm going to go ahead and bring it up what the answer is. So how you should have understood this is that the negative end of CH3F is with what atom? It would be the chlorine, right? And the other side would be the positive end. And you can just write it like that. Negative, positive. Don't overcomplicate your life. One side is negative, the other side is positive. And then we orient water. Water has a negative end, that's going to be the oxygen, and the positive end is always hydrogen. So we're going to want to face, because I have space over here before I'm choosing this side, I'm going to face my hydrogen towards fluorine, right? All I have to show is a positively charged hydrogen, or partially positively charged hydrogen is attractive to negatively charged fluorine. And then I'm going to write my attraction, which is here. This is the intermolecular force. Now, question for you, and you're going to want to write this down. If you didn't, you will want to write this down because this is a trap. I'm going to ask you a question. Is this dipole-dipole, or is this hydrogen bond, this dashed blue line? Which force of attraction is it between these two? That's the wrong force. It's dipole-dipole. Let's be clear.
That's a trick question. I feel we could.
In order for you to have hydrogen bond, both molecules have to have hydrogen directly connected to fluorine oxygen or nitrogen. This chlorine is attracted to is directly bonded, to a carbon, not a hydrogen. So if this was HF and H2O, that is a hydrogen bond. But because this is carbon connected to fluorine, it is actually a dipole-dipole. So you're going to want to write that down or have that in your notes because that's a trap. For hydrogen bonding, your molecules participating in the hydrogen bonding have to have hydrogen directly connected to the fluorine, the oxygen, or the nitrogen. Yes. Yes. All right, so we're almost done. We're going to take a look at one more thing, and this is just what are intermolecular forces important for. And then we're going to do a time to climb. So, I've already said this, but I wanted to bring it up because this is where we're going in the future lessons, like starting next class. Why is this important? Why did we go over this today, looking at the molecular level? So it turns out the stronger intermolecular force, the more energy is required to separate molecules from each other, because if they're more attracted to each other, it's going to be harder to separate them. So this actually goes into molecule state of matter, whether they exist as a solid, a liquid, or a gas. And what temperature will be required to melt and boil different materials. So that's one of the things. And the second thing is that compounds with a stronger intermolecular force, these have strong force of attraction, so this means that they will favor a more condensed state of matter. And so that's also important. One of our lessons before winter break is going to be on states of matter, but a deeper dive than you've ever done. You've learned about solid, liquid, or gas, but we're going to be looking at the particles a lot deeper than that. And that'll be something that we're looking at before the break. And so the intermolecular forces has everything to do with state of matter, and also if compounds are soluble or not in water. And so that's where we're about to be going, is into a topic called mixtures, solutions, and states of matter. So this is kind of a bridge lesson, where we were at to where we're going. Now on Nearpod, there's going to be one final exercise. This is a time to climb, which means it is a competition. So time to climb. I'm going to give you a little bit of time to choose we're picking happy holidays. We've done it before. I'm pretty sure we have. So I'm sure we've done time to climb before.
Oh, those, yeah.
Pick a character. I'll give you a minute or two to decide your character, and then we're going to do some practice questions. As you're working through the time to climb, I do have your, I like to call it homework. If you can't finish it in class, it's homework. So homework. I've got 9 students connected. Please make sure you're picking your character in the next 90 seconds. There's penguins, there's turtles, there's bears, there's giraffes. Apparently there's octopus. Yes. They're in the front of the classroom. Whatever I have is in the front and in the back.
I did not know new generation of penguins have 4 arms.
4 arms.
Yeah, maybe he showed us an octopus and said that was a penguin.
Maybe they just want this shit.
30 seconds. Pick your character.
Maybe they're penguins from Chernobyl.
Make sure you're choosing your character.
What would you call a flock of penguins?
Make sure you choose your character.
You just said.
No,
Flock of penguins.
No, like how you know how certain birds or species, when they're together, they have a certain meaning that they're put under.
Finalize your character. You've got 15 seconds.
If it's a group of ravens, it's called that. Yeah, bird.
All right, 5, 4, 3, 2, 1. Hitting start now. Three, 2, 1. All right, first question. What is the shape of BF3? Uh-oh. I did give some time. I'm going to pass out the homework. This is due at the beginning of next class while you're working through the final activity for the Plenty. Fortunately, no, not on time to climb.
Bottom of that.
It doesn't even give me the option with the toggle to be able to let you do that. This is the homework. Make sure you put it away. It's due at the beginning of next class. When you take the test, wait,
I saw
did you
doing
not
it, I
put
just
your
called it. Yeah. And it was like, yeah.
I don't want to take it from you because you need it for your notes.
Yeah.
So just
Oh, shit.
drop it by your.
It was trying to.
Oh, what is the bond name? Should have forgotten all this. Contest is a couple days ago, right? Mary, shall I put yours at your desk? I did give time for you to draw it out. With time, yes.
Whoever does it first and gets it right.
Yep. That is the way it works. Let me make sure I'm turning off the recording before I forget.